Hi everyone. Thank you for your interest in this session. So, in this short talk, I would like to take you through the different challenges that we have in inferencing large language models and some of the ways to tackle them. So, by the way, I'm Logesh Kumar Umabati. I'm a lead machine learning research engineer at Sama Technologies. So, I lead the machine learning efforts for one of the products there. And my research interest includes code generation and adapting large language models for biomedical and healthcare domain. So, as they say, to s- to solve any problem, first we need to understand it better. So let's try to understand the inference, the whole LLM inference problem. So here, uh, one of the reasons for the challenges that we have with LLM is its auto-regressive nature. So by auto-regressive, what I mean is, as it's illustrated in this beautiful animation from JLMR's blog post. So here we give a bunch of text as input to the model, like recite the first law dollar, and once this bunch of text is called as a prefix or an input tokens that we give to the model, and based on that, the model auto-regressively generates tokens one by one. So you see that the first A is generated, and that A goes as an input to the model, and then it generates robot, and robot goes as an input, and so on. So this type of one token at a time generation introduces some challenges in LLMs. So in the previous generation of models, usually the encoder-based model, uh, we are mostly good if we are able to like fit uh, a number of examples or sequences in a single batch, since all the parallelization that is involved in batching would mostly take care of that. But when it comes to LLMs and mostly the decoder-based LLMs, the auto-regressive nature of it uh, uh, gives us certain challenges. So let's probably dive deeper through one by one. So one of the challenges is with the auto-regressive nature of it, as well as the uh, the whole paradigm of LLM is that so there is a big clue in the name itself. It's large language models. So the size of it is one challenge, and apart from that, like I said, the auto-regressive nature of it. So this is an illustration of the self-attention mechanism. So whenever we have an input, for each of the input, the model has to create a query vector, key vector, and value vector, and this is just for one token. And these vector needs to be the matrix needs to be created for as many heads and layers that we want. And if we are going to generate it for a complete sequence, that gets added up pretty quickly. And this is a bottleneck, because if we want to generate a longer sequence, this could quickly add up to a lot of memory that we need. So that could impact our the amount of sequence that we can generate. So there are two ways that we one can go about it. That is, one can trade off memory instead of computation. So usually this we create a KV cache. So as and when the tokens are generated, we try to cache those particular tokens KV into the memory, so that we trade off memory instead of calculation that we do when each tokens are generated. But this introduces new challenges in terms of handling the memory. This KV cache adds up quickly. So probably we'll see the math of how this KV cache builds up and what are the ways to handle this. So the numbers behind the inference problem. So whenever we say a model of certain number of parameters, we would need to like have a quick thumb rule to understand what would be the memory requirement of that particular model. So the quick thumb rule is it all depends on the it all depends on the uh, floating point precision that we have the parameters in the model. For example, the FE32 32-bit model would take like 4 bytes per parameter. So let's say if it's a 7 billion parameter model, then 4 bytes it would take like around 28 GB for just to load the model into the memory. And similarly, for an half precision or FP16 type of model, it would take 2 bytes per parameter. So it will be like 14 GB of memory. And for int 8, so it's just 1 bytes per parameter, and into number of parameters would be like just 7 GB of VRAM. There can be certain overhead over that, but approximately it would take like this many number of VRAM to be for each of the individual models. So we saw how KV cache like quickly adds up. To give a number to it, so the way we can calculate the KV cache is this. So uh, so we have like 2 multiplied by 2, and then into number of layers, number of heads, and then the dimension of head. So this KV, the key value matrices, is present in all the layers, and it is also replicated across all the heads of a transformer model. So that's why we have n layers into n heads, and this is the dimension of the matrix. So that is the embedding size of individual head. So this is a D head, and why we do first, the first two denotes that we have two matrices here, K and V, key and value matrices. And the second two denotes the, let's say this assumes that this is an FP16 based inference. So 2 bytes per parameter. So that's why we have this calculation. So 2 into 2 into number of layers into number of heads and D heads. So this should give us an idea of how much memory that is required to inference just one single token in a batch. So to give an example, let's take an example of star coder, a 15 billion model. So for that, an FP16 inference from the formula that we saw before, it would take like approximately 30 GB of memory. And for a equivalent multi-head attention like model, the KV cache from the formula that we saw before to take like 4 times, 2 into 2 times. So this model has like 40 layers and 48 heads. So 40 into 48, and then individual dimensions of the head is 128. So it would take roughly about 0.0098 GB per token. So this might look a lot smaller, but when you add up to the number of batch size that we have and the sequence length of 1,000 or 2,000 or more than that, this quickly gets added up. And when it comes to multi-query attention, so multi-query attention is where we reuse the KV cache across different heads in the layers. So in that case, the amount of memory required is getting reduced the number of times by the number of times the number of heads that we have. So here is just at 0.002 per GB. So to give an idea, to fit this model into an A140 GB, so we already have utilized 30 GB in loading the model. So the remaining is 10 GB. So to inference just one token, we would need a 0.0098. So in essence, we would be like able to generate 4,000 tokens approximately, and that would, if you convert that to a batch of 1,024 tokens, it would be somewhere around 10 sequence length per, 10 number of sequence per batch. And for multi-query attention, it's like you can generate as many number of tokens as multiplied by the number of heads that we have here. So here it is closely like 200,000 that we can fit in. And and that gets into like 480 batch size or 1024 tokens. So to have an optimum inference speed, MQA is better, and then there is group query attention, which instead of using just one KV matrix per layer, they use somewhere around more than one to less than the number of heads of KV matrices, and that gives us a speed up, and that also matches the quality of generation compared to MHA. And then MHA is the most memory hogging attention mechanism. So now that we know what is causing the one of the challenges that we have in inference, let's see how we can quickly handle that. So one and before that, whatever that we saw now is about the memory requirements during the inference time. Like if you are interested in understanding the memory requirements during training time, you can check out this space, wonderful space, where if you give a model, a Hugging Face model repo, they would show you the amount of memory that is required for training. So now that let's see certain techniques that we can do to handle this. So one of the probably the popular technique is flash attention, wherein so in the paper flash attention, fast and memory efficient exact attention. The authors have introduced this technique wherein usually the GPU's memory is in hierarchical nature, but the current architectures that we have, the way the transformers have been implemented, did not have been taking advantage of this architecture. So flash attention has introduced a novel way to take advantage of it. So here, like we have a hierarchy of memory. So in a GPU, so HBM is a VRAM that we see in GPUs. So and then we also have SRAM, but the SRAM is much faster. Like if you see, it's about 10 times faster, 10 times also more than that faster than the HBM memory. But the cache that is the memory that we have capacity is lot lower. So the authors have devised a way to tile the attention matrices that we have, and then do most of the calculations in SRAM so that it's much faster. And then they reduce the number of input output the transactions between the memory, so that way the whole inference is the attention is calculated much faster. And the other technique that they have introduced is also they have also done optimization is also the fused kernels, where they have fused multiple operations into one, as you see in this graph. So based on because of this, there is a lesser number of uh, transaction that needs to be happen between different parts of the memory, and the IO is reduced drastically. So this speeds up the inference. So this speeds up somewhere about at least twice the speed up that we have without using a flash attention. And the attention is also it does not have any quality impact to our model generation. So we can plug in flash attention and get the same amount of quality generation that we are previously getting before introducing flash attention, and at the same time do a faster inference. So there are multiple ways we can make utilize these features. One is using transformers and better transformers. So we can initialize a model as we usually do with auto model for causal LLM, and the same tokenizer and pipeline. So one difference that we have to do is model dot to better transformer. So we are porting the model to a better transformer, like uh, a better transformer instantiating to that library. And then so this other Torch backends are CUDA SDP kernel. So this utilizes Torch's SDP kernel, which has flash attention built in. So we just need to say mention that enable flash equal to true. So from now on, whatever the text that is generated would be done via flash attention. It would be much faster. And another way to utilize flash attention is by using text generation inference library from Hugging Face. This is a most intuitive and easy to start library for faster inferencing, and it is also a kind of state of the art in terms of inferencing LLMs. So we can just do it with a Docker command, wherein we do Docker run and to that particular text generation inference image. And when we need to pass the model ID, the model of the model from Hugging Face, and we are good. So the if our model is supported as with flash attention in any of this list that is given here, our model would be able to load with flash attention, and we would be inferencing in a much faster speed. So yeah, so that is about flash attention. So the flash attention took advantage of the input-output challenges that we have with attention. So another technique that solves the overall LLM inferencing problem is the page retention and continuous patching, introduced as part of the VLLM library and paper efficient memory management for large language model serving. So in this technique, so you traditionally when we have like a bunch of sequences that we want to inference in a batch on an LLM. So traditionally, the KV cache has to be pre-allocated to the size of a max new tokens that is expected in a batch. Let's say if a max new tokens that we set it as 1024, then the KV cache has to be pre-allocated for the whole 1024 tokens. So, but that would not be an ideal case since some of the sequence in the batch might end a lot sooner than 1024 tokens, and some of only probably a few sequence could reach the 1024 tokens. So in this scenario, we are optimally allocating the whole KV cache, which is not required. This is also hogging the memory. So the authors of this paper came up with an approach where they used traditional OS operating systems paging like mechanism, wherein they used a KV cache as blocks. So they allocated the KV cache in a blocked manner so that they don't have to give a contiguous set of memory to the particular KV cache. So they can dynamically allocate whatever that is only required. And so even if a sequence is going to end up a lot sooner, they don't have to like allocate a full sequence length of KV cache to it. So that was one optimization, and then the continuous batching. So again, during a batching that is involved in auto-regressive decoding. So even if a batch size is lot longer, let's say if a batch size is like 256 of size, but not all the tokens would go on till or complete it together in a batch. Some might complete it sooner. So the traditionally the complete batch has to wait for the new batch to be loaded. With continuous batching, they introduce a method where they can, even if one single sequence get completed, they can fit in another sequence in the same batch and continue with it. So by this way, we can utilize the optimization that comes as part of batching. At the same time, we are not waiting for the whole batch to be completed. So this was these were a few of the optimization that was introduced. So because of that, the throughput is improved when it compared to, so this is from the original benchmark. So when they did a benchmark on 840 GB Llama 13B, so they were getting like 2.2x to 2.5x speed up on TGI, and the 25 to 14 to 25 times speed up on vanilla Hugging Face inference. So this, because of the paging mechanism that we discussed earlier, they can do the parallel output completions. So for the same input, if we want to like change the temperature and generate the num sequence, if we adjust it, it will generate multiple sequences. So since the KV cache is shared in a blocked manner, so they would be able to share the memory across different sequences, and they would be able to like further speed up when we generate multiple sequences per input. So this is when we generate multiple sequences per input, they are like 3.3 to 3.5x faster than the TGI and 8.5 to 15x faster than IBPs. So how to get started? So this is a library, so we can install pip install VLM and then follow this step. It's very intuitive. Uh, we can initialize the Hugging Face model with just LLM model equal to this. And then when we give prompts to LLM to generate, it starts generating. So they also provide an API server. So we can call the API server with this command, and that would instantiate an API server. Then we can do a API request to that service. Yeah, they do continuous batching during the API, the request handling phase. So another technique to speed up inference is speculative sampling. So when we discuss about the autoregressive method, so the prefix that we give as input can be processed a lot faster than the individual tokens that we generate afterwards. The reason is the prefix can be parallelized, and since we pass in a bunch of tokens, the whole calculation can be parallelized. And if it's in a batch, the further parallelization can happen to it. So the authors of speculative sampling are like taking advantage of this difference. So they want to like instead of a bigger model to sample each individual tokens auto-regressively, they want to make the model to, instead of sampling it, they want to make the model to prefix it, handle everything as a prefix. So what they do is they have a smaller model which has the tokenization part. Let's say in the paper, the authors have taken like a 70 billion model, and the smaller model they have taken a 7 billion model, and the 7 million model does the auto regressive decoding, and whatever the auto regressive decoding that is done by a smaller model is passed as a prefix to the bigger model, and the bigger model selects if that prefix is correct, and if it's correct, it just continues from there. So if it's correct, we reduce the time taken because prefix is usually processed faster, and this way the authors show like 1.5 to 2 times improvement in the speed up of the inference. So this is comparing, the authors compared a 70 billion a target model with a draft model. The smaller model has 7 billion. So they were able to get like somewhere close to 2 times to 2.5 times the speed up. Excuse me. Um, so, so the requirements for a speculative sampling setup is that we should have a draft model which has the tokenizer, so that whatever that is suggested, logics that are suggested by the base model would make relevant for the target model as well. And the draft model should also be of a smaller size, which can speed up. The auto-regressive nature should be a lot faster than the target model. At the same time, it should also be of a size that it can be accurate in generating the tokens for the target model. So the intuition here is when we generate, probably not all the tokens require a computation that is required for that needs a bigger model. So some of the common phrases, some of the most repeated phrases or easier to predict phrases can be offloaded to a smaller model. So that's the intuition of this approach. And this speculative sampling is being integrated into many of the popular libraries like VLLM and text generation inference. There are works that is going on to integrate it. But for now, there is an independent implementation that is done by this repo, Shreyans 26. So you can probably use this to see the difference. So the author show that there is a 1.5 to 2 times difference with this approach. So another popular optimization that can be done is quantization and parallelism. So with the math that we saw before, the memory that is required to load a model depends on the precision of the model weights. So here, if we can quantize the model to int8, we are like reducing the size that is required, the RAM that is required by 4 times. And if it's half precision, we are reducing it by 2 times. So there are like different quantization mechanism, LLM, int8, GPTQ, and other mechanism. I'm not going in detail of that, but quantization reduces the memory so that you can fit in lot more sequence length as well as lot more batch size into a same amount of GPU that you have. By that way, the throughput can be much better in a laptop. So one example is this. So if so in King phase, you can do this by installing accelerator and bits and bytes library along with transformers library. Once you have done that, uh, adding a parameter load in 8-bit equal to true or load in 4-bit equal to true would load the model with that precision. And you can see that here the 7 billion star coded base model takes about 15 billion in memory. But when we load it in 8-bit, it just takes somewhere around 7 billion of memory. And so one more so this is and then so in text generation inference library that we saw, we can enable that by these flags, quantize bits and bytes or quantize bits and bytes. We can even do 4-bit on the fly quantization, loading and quantization with bits and bytes, NF4 and FP4. So this way we can load the model in a lot lesser memory, and we can do the inference on it. But one catch is that when we do this, usually the on-the-fly inferences, they tend to be much comparatively slower to the half-precision inference that we do. And then we can also parallelize it. So another way to increase the memory that we have for generation is to have more GPUs uh, provided. That can be done by tensor parallelism and pipeline parallelism. So text generation inference supports tensor parallelism. So we just have to mention the number of shards that we want our model to be loaded as, and also the memory that is shared across these shards. So one other naive way to parallelize or utilize is by using accelerator library. So one other challenge that we have with the large language models, probably if you are trying to load it for a toy use case, you'd have noticed that the amount of time it takes to load a model is a lot longer, since there are like multiple copies of the model getting transferred between our CPU RAM and then to the GPU RAM and so on. So this is optimized by the accelerator library. So if you have installed accelerator along with transformer, if you do device map equal to auto, the loading time would be a lot faster. Like here, it initially loads in like 86 seconds, but here it's just take 20 seconds for the model to be loaded. And not only that, it also like does a naive pipeline parallelism. So it parallelizes your model across the GPUs. Even though that's not an optimized version, text generation inference does more optimized version, but still it does some initial optimization, and you would be able to utilize the parallelism and with accelerator and transformer library. So that's pretty much I had, but I would like to acknowledge some of the resources that I've used for this talk and also used in the past to give me this information. So these are the blog posts. Multi-query attention is all you need, the paper, and then the efficient scaling transformer inference. And one other paper that we would highly recommend is Transformer Inference Arithmetic, where they have explained in detail the different math that is going into the inference process. So I'd like to acknowledge all these blog posts and papers, and apart from the ones that I've already cited. So yeah, thank you. That's brings us to the end of this talk. So if there are any feedback and questions, this is where you can reach me. And this is where the slides are available. You can access the slides here. Thank you.